Okay, let's start. Good afternoon, everyone. Thank you very much for joining us for this online technology meeting. So today we'll cover the interesting topic of optical design simulation and especially the digital twin. So I'm Jeremy Pico-Clement, I'm technology specialist at EPIC, and I will very quickly introduce what is EPIC to you if you doesn't know. So EPIC is the largest industrial network in the world in the field of photonics, industrial photonics, with today more than 850 members. We cover all the value chain, of the photonics industry, from the component manufacturer to the design prototyping company, and we also include some end user and system integrators. We also cover all photonics application, which is quite wide. So we come from, space, defense topics, to quantum, biomedical, including AR, VR, agriculture, etc. Everywhere you can find photonics, we are covering this topic. Our aim is to create a sustainable European photonics industry, and how we do this. So we provide several different type of services to our members. So technology support, market and technology report, networking opportunity during a physical event, mainly access to markets. If you want to go to the US, to the Asia, we're able to support you. Mentorship, human resources support with the website Jobs in Photonics, and also investment support. Few words also about the next EPIC events we will organize. So as you may already know, we organize a physical in-person meeting and also online meeting. So about in-person meeting we are this week actually in Germany. Some colleagues of mine are there at Atieh covering quantum technologies topics. We'll be in China in September for CIOE. We'll be at ECOC. We'll organize something at Quantum Effects. We'll be in October at ESILOR-Luxottica covering the augmented reality topic. And in November, we'll be at Amplitude Laser close to Bordeaux in France, talking about laser technology. About online meeting, we cover not only technology, we cover also other kind of topics like marketing topics, communication topics. We have also an event which called EPIC Members New Product Release. So if you have a new product in the pipe, you can also get more visibility and participate to this event. And we have also some online technology meeting on optical connectors, optical communication for space, laser processes, etc. Also, a quick overview of the companies that are registered for today's event. So as said, we cover all the photonics value chain, end users and integrators, research and development centers, component and modules companies, metrology and testing, materials consistency, equipment manufacturer. So as you can see, we cover all the value chain. And about the agenda of today's event, so we'll have 6 speakers. So thanks, of course, to them for participating and sharing this presentation. So we'll start with Flurin Herren from Synopsys, continue with Ahmad Atieh from Optiwave, then Oliver Faehnle from PanDao, Nikola Nedovic from NVIDIA, Lieven Penninck from PlanOpSim, and we'll end this meeting with Dominique Bonnisseau from MIMOPT. So thank you very much again for your participation. So it's an active discussion, I would say. So after each presentation, we'll keep some time for questions. So you can raise your hands through Zoom. So do not hesitate to do it. You will have time to ask any question that you have in mind. After each presentation, we save 2, 3, 4 minutes for this. So thanks again. And now I would like to give the floor to our first speaker, Flurin Herren from Synopsys, Senior Optical Manager. And the title of your presentation, Flurin, is Optical Digital Twins for Semiconductor Manufacturing with Zemax Optic Studio. So welcome, and please, Flurin, the floor is yours. You can start.
Yeah, thanks. Merci, Jeremy. Let me share my screen and go ahead. And I'd be thankful, Jeremy, if you could quickly confirm that you can hear me all right and also see my screen.
Perfect.
Perfect. Amazing. Okay. Yeah, hi and welcome everyone. Very, very, very pleased to be here. I think these epic conferences are a great opportunity to share knowledge across the industry. So yeah, really pleased to be here. My name is Flurin Herren. I'm a optical and optomechanical engineer here at Synopsys. I've joined Zemax back about five, nearly 6 years ago now. And then obviously went through the acquisitions and mergers, and now we are ANSYS, part of Synopsys. I wanted to speak today about digital twins specifically for semiconductor manufacturing, but that's kind of the last stage where we end up. So I wanted to build up a bit what we can do within the optics and beyond add ANSYS for digital twins. The agenda is the following. So as I have the pleasure to be the first one, I actually thought this is going to be redundant, but having the digital twin, explaining what is a digital twin and its value is probably quite good to start with. Then I wanted to explain the ANSYS digital twin ecosystem, the key technologies, and then I would like to build it up from the entity level. So give an example for Zemax, but also for Spears. And then I'd like to go to this level 2, which is kind of the process level. And that's where I wanted to end up in today's main topic, which is the semiconductor manufacturing, and look at an example for a manufacturing process and how we can look at digital twins within a full manufacturing process. First of all, I'd like to start with the kind of the obvious question, which is what is a digital twin? So a digital twin is an integrated data-driven virtual representation of a real-world entity and or a process with synchronized interaction at a specified frequency or fidelity. And that's kind of a quote which I've taken from the Digital Twin Consortium, because I think it kind of it's a really good one sentence to explain really what it's all about. So we're creating a digital representation of a real world entity or process, and that entity or process, and process is kind of the big word here, is not only one thing, it can also be a process, i.e. in a manufacturing process. An example here would be a sensor is mounted on a certain device and it's feeding information back into a digital model. So we have kind of the asset which is mirrored into the digital world, and that obviously gives us great value. We can create virtual sensors. So if you would explain a physical sensor, you would be able to you suddenly would be influencing the measurements, but a virtual sensor won't do that. We can perform what if applications and so on and so forth. So it gives us a lot of good and interesting benefits creating a digital twin. Now, the main key technologies which we need to consider when we want to enable digital twins is multi-physics simulations. So we need to have a good way of simulating our usually multi-physics problem. We need to reduce order model because we need a certain speed of our simulation, and full scale physical simulations are sometimes just too slow and can't keep up with real-time dynamics, which we usually would need. So reduce order model are a very integral and important part for digital twins. Then we need obviously real-time data integration. So we need also sensors and information coming from the from the real asset or the real process, but also historical data which we can feed in. And then fourth kind of key technology, which are listed here, is kind of using AI and machine learning, because then we were able to start creating a prediction behavior and can go even look into the future and do some advanced prediction based on the information we gathered in real time. So these are kind of the full key technologies. And then, so how does the ANSYS environment fit into this? So this is kind of a really, I really like this view because it kind of shows what ANSYS is all about. So the foundation at the bottom, we have the physics-based simulation, and we have all of these. And just above here, we have the digital twins, which feed into all of these physics. So the multi-physics approach is covered in great extent. We can create reduced order model with our multiple process and data management and optimization tools, such as OptiSlang, for example. We can use our AI tools to create prediction models. So we have basically all of the key technologies covered within the whole ANSYS suite. And before I jump onto this, Jeremy, could you just give me the time? How are we doing for time?
It's okay, no worries.
Okay,
Yep.
sounds good. Okay, you just let me know, yeah? So if we want to now employ the full ANSYS suite on top of a digital twin summary, it would kind of look a bit like that. So we need to first create the physics-based model, and we can use our physics solvers for that. We create a reduced order model because we usually only want input to output. So we're looking at a very specific sub-entity of our problem. And feed that into a system simulation for our process or integration. And then we can create an EOT, so Internet of Things, to deploy our digital twin, and that kind of stays then connected with the real asset over time, and is also gathering final data as well. And we can obviously create this as an exporter platform in a agnostic container as well. So this is kind of the full opportunity and the full possibility and capabilities that we have within the ANSYS suite. But I wanted to now build it up in 2 levels. So I wanted to look at a bit more simpler example, specific entities, and then go to our main topic, which is the manufacturing process of semiconductor as a specific topic. So the first entity example, which I've gathered here, would be kind of, let's take a microscope objective. So here we have a microscope objective. What we're doing now is we're building up a digital microscope from this physical setup here. We're creating this within ANSYS ZMax Optic Studio. So AZOS stands for ANSYS ZMax Optic Studio. So the abbreviation of ZMax or just Optic Studio, depends a bit what terminology you're using. And this is effectively our digital twin. Now, recreating a Microsoft objective would kind of allow us then to reproduce its performance. And once we have that performance and we digitalize that performance, we can then go ahead and look into can we somehow optimize the system. So once we have it digital, we can then say, okay, what if we change the last lens, for example, and we can make already design decisions before even going back into changing anything on the real prototype. And that's already the first step of digital twinning, because we're creating a digital representation of our real asset. And then we say, okay, if we change and tweak some things, then we can see how performance is changing, and then we can feed that decision and that information back into our real life application. For here, for example, and that's a nice cross reference to another presentation later in this conference from PanDao, from Oliver Faehnle. For example, here we could export the lens, the last lens, for example, and we could use PanDao to see, okay, from a financial standpoint and from the manufacturing, is changing this lens maybe cheaper, and we get better performance, and we can make some design decisions and go and bring this design decisions back into our physical application. Another interesting use case, for example, as an entity example and not as a process example yet, would be a physical representation of an image camera. So an imaging system, for example. Let's take an imaging system. And what we can do, we can include the housing from this physical imaging system. We can even include some test bench results and then bring this into, for example, Speos. Within Speos, we can then regenerate and represent the whole physical imaging system as a digital representation. And once we have this digital representation set up in Speos, we can then have the full capability of running comparison campaigns. So a comparison study for all kinds of things. We can then also play with the sensor, for example. If we want to have it fully digitalized, we can start changing things first on the digital twin. And it just gives us the capabilities of playing with a real imaging system in a digital sense before even touching the physical system. So another neat way of using the ANSYS optics tools, ANSYS Emacs and ANSYS Speos here in this example, as a digital twinning approach for specific entities. But what if we now would want to look at a whole process? And that's kind of where I wanted to finally end up with my presentation here. So this process could be deployed within semiconductor manufacturing. So how does this bit more complex looking plan kind of break up? So we have a physical system on the left. Our physical system, for example, could be a lithography for a semiconductor manufacturing. And we are having here, for example, also, if we have lithography, we have a lot of infrared radiation, and that influences, for example, the optics which are used in lithography. So what we want here is we want to use a stop analysis, so structural, thermal, optical performance. So we want to look at the influence of that infrared radiation on our optical mirrors in this case. And what we have here is we have the physical system here. We are bringing the analytics back into the analytics manager. And here we have our EOT platform. So this is deploying and gathering actual input from real assets, so from our physical system, but it's also deploying a virtual sensor, which we built in, and keep on checking the performance of the mirrors due to that infrared red radiation. And based on that, we can generate a real-time visualization and an optimization operand, which we could then do modification on top of our physical system and our physical process again. Now, how is this built up in the first place? So we're using a digital twin platform where we create a simulation where we do stop analysis. So we're recreating the system. This in this case here would be the optical system. So we're recreating the optical mirrors. We're generating the data in order to have a deformation due to that infrared radiation. And then we're creating a reduced order model based on our simulation so we can run it in real time. And then we have a system model for that manufacturing. And that system model is then deployed into our runtime here and feeds into our IoT platform, which essentially then is also bringing information back into our physical manufacturing, but also get information back into our IoT platform, which essentially also feeds information back into our field data, which can also influence again into the system model for the manufacturing process here. Additionally to that, we could also deploy the reduced order model for machine learning using Twin AI to create prediction models on top of that. And then we can have a new kind of dimension to the workflow as well, where we can bring in prediction models and also catch some maybe failures or stuff like that. So this was kind of a way to show you our optical solutions, mainly ZMAX, but also not only ZMAX, because I didn't want to just stick with ZMAX. And then how we're using that to deploy first on entities, but then also on a process level, how we deploy digital twins. Apart from our optical models here, obviously for a stop analysis, you would also need ANSYS mechanical to generate the structural deformation. And also for the reduced order model, you can either use directly ANSYS Twin Builder, but you could obviously also use OptiSlang, which has great reduced order model capabilities to break the simulation down into the essential parts to simulate the data as quickly as possible. And that was already it. I hope I was all right on time, Jeremy.
Yeah. All good.
Sounds good. Perfect. All right. Yeah. In that case, I'd like to open up for questions now.
Yeah. Thank you, Flurin. So, any question for Flurin? You can raise your hands through Zoom. I have a question for you. When when you convert your 3D physics models into your ROM, what are the typical drop in fidelity? What do you lose in terms of information? Do you have losses or is it very accurate?
It's a great question, and it depends heavily on the physics itself. Some physics, for example, are quite fast in predicting from a simulation standpoint of view. So there are even situations and scenarios where we actually can use the full physical simulation. But like computationally heavy stuff like structures or fluid dynamics is always usually reduced order model. And there is the case that there is some loss, but if you target your reduced order model, because you'll never get to the accuracy of actually simulating the data completely, but the loss is usually accounted for. And if you do it, if you create a reduced order model the way that the very specific way it's needed, and you're not changing any parameter drastically, it's very sufficient and very close to the actual prediction.
Okay, thank you. Yes, Oliver, you have a question.
Thanks, Flurin. Very nice talk. Really cool.
Thanks.
I enjoyed it. One question out of curiosity. So you basically showed that you have digital twins, then you combine them to bigger digital twins, so to say. So you get more abstract. So you reach levels of higher abstract working, so to say. And your local digital twins, you check in reality from time to time. And how do you check the upper, more complex systems digital twins? Do you check them on their level of abstraction, or do you go back down and feed that up vertical or horizontal?
Yeah, exactly. I think you have already kind of responded to that as exactly that. So on certain complexity, it's obviously hard and it's not even make sense anymore to trying to predict the whole process. You need to really break it down in subsystems and sub processes at some point. And there you can do verification steps and do in a certain frequency. You can verify your own predictions, but you can't really do that at the highest level when you have a bit more of a complex or larger workflow. Exactly.
Thank you, Oliver. And yes, Lieven, last question.
Oh, sorry. Yeah, thanks for the presentation. I have a question more about the reduced order model that you built. You build this on some representation, but over time your system would drift, I assume. So do you have any sort of recommendations to prevent that from, as your system changes over time, your model would become less accurate? And how can you detect and, if possible, adjust for that?
Yeah, that's a very good question. Thank you. Yeah, so exactly, you basically would need to account for the reduced order model has only a validity for a certain time frame. So after a certain step, you would need to evaluate your reduced order model and then, if possible, re-simulate. But the nice thing is, what you can do is, while your reduced order model is running, you can always have a simulation running in parallel, and essentially then creating new reduced order models, which may account for a slight drift in the manufacturing process. And that's also, for example, why you would bring in real data. Because if you can see a drift, we can maybe already have a function in a parameter of that reduced order model to account for that drift. Because the drift is usually predictable is the wrong word, but it's foreseeable in some way. So you can already have a bit of a lever installed if you want to account for that drift.
Okay, thank you for your question. And let's thank Flurin again. Thank you, Flurin, for your intervention. Thank you very much.
Pleasure. Thank you. Thank you, Joe.
Now, let's welcome our next speaker, Ahmad Atieh, VP Optical Systems at Optiwave. So, Ahmad, the floor is yours.
Yeah. Thanks, Jermaine. Okay, hello, everyone, and thanks for attending. I'm going to talk today about OptiSystem software enabling photonic integrated circuits. So mostly I'm going to concentrate on photonic integrated circuits and talk mainly about how to go from the mask layout into system characterization. And my name is Ahmad Atieh, and this work has been done with my collaborator, also Scott Newman from Optiwave. Okay, let me put this pointer here, and then let's go. Okay, so I'm going to talk about and give you an overview about Optiwave, and then show you the product line of Optiwave. Then I'm going to talk about the flow for the big transceiver design. So we're going to go from geometry to device level modeling, then optoelectronics modeling, and then system characterization. Optiwave is established in 1994. It's located in Ottawa, Ontario, in Canada. And what we do basically is we do software design tools. So this software can be used for designing or simulation or optimization, any devices or links or system, or as well as networks. The advantage of software, basically, it can shorten the product line and also can improve your quality, as well as it can improve the cost effectiveness and productivity. The product line of Optiwave can be categorized in 3 levels. One of them is the system level, and the OptiSystem software and OptiSPI software, which is an optoelectronic software, are the main software packages. And then we have the component level software, which you can design devices using, for example, FDDT or OptiOmega, which is a new software we introduced to design photonic integrated circuits. And there is mode solvers, which is called OptiMode, in addition to other software packages like, for example, beam propagation method, optical fiber, which you can design any type of fibers, as well as OptiGrating, which can be design fiber gratings or waveguide gratings. And the last one is the instrumentation software. And this is where you can communicate with equipment from any vendor. It's not dedicated for any vendor. And you can, this equipment can be remote or local to the software. And you can control the equipment, you can automate the operation of the equipment, you can set parameters, and you can run setups, then collect data, and you can process the data within the software, or you can do it externally. So you have the both capabilities. Now, this is a kind of general view about the company. We are over than 80 countries. Our product, we are in business over 32 years, and our product in industry, companies, in universities, research, and governmental institutions. And this is a snapshot of some of the industries and universities and research institutions over the world. You can download our software for free for 30 days. So you can go to Optiwave website, and then you can go to the download page and click on the 30 days evaluation. And then you need to register with your email, work email or university email. And then eventually, once you register, you can download any of these 9 software packages I mentioned to you. And the software can download on the C drive on the program files and then Optiwave software folder. Very good resource here for knowledge. We have the YouTube channel, Optiwave High Definition channel. And there you can see, view lots of videos which can give you introductory about the different software or some applications. Huge library there. You can look at it and give you a resource for understanding the software. In addition, you have on our website, there is a knowledge base where you have lots of reproduction of papers based on experimental data, where we feed always experimental data into our models to validate it and make sure that the user is confident about using the software. Now I'm going to move into the main topic of the presentation, which is mainly how to design photonic integrated circuits from JDS masks into system characterization. And the flow is going to be this way. You create your JDS2 mask using a software, third-party software. We are collaborating with many EDA vendors. One of them is Lucida. I'm going to talk about it a little bit more later on. But you have the JDS2 mask, and then eventually, once in Optiwave software, we read the JDS mask, you have the layer information, the material, and so on. And then we move it into the device modeling, where we generate S parameters. And these S parameters can be read into a software or optoelectronic software. You can do the simulation there, create either netlists, which this netlist can be read by the system software and do the system characterization. So this is kind of the flow which we see here to demonstrate in for transceiver PIC design. Now, this is the general components and JDS2 masks for the ring resonators, for example, or the modulators, as well as the multiplexer side and the demultiplexer side. So this is all of that JDS mask has been used in this software, and then you can extract S parameter matrices or netlists, and then we can use them in this system characterization. So the first part here, beside the JDS mask, is the device level. And the device levels, you can use different software packages in Optiwave, which is OptiOmega, which is dedicated for photonic integrated circuits designs. And then you can use FDDT to do the simulation. You can use also the beam propagation and Optimal. As you can see here, you design MMIs, you can design ring resonators, waveguides, bends, and phase shifters. Anything you need to do design, you can simulate within the software. This is the structure of the OptiSpice like representation of the modulators, like, for example, how we use the design in OptiSpice. And then eventually, as you can see here, there's the modulator, 2 modulators right now here, and then 2 rings. And then you can run the simulation and create netlist and then pass it to OptiSystem software, where you can go into the next phase, which is the system characterization. Now, in the system characterization, OptiSystem software, you can integrate any type of modulation in the market externally to your PIC, which you design. And then eventually you can do system characterization, where you can look into, for example, BR analysis. You can look into constellation diagrams, spectrum analysis. All of that is actually, in fact, OptiSystem software has over 630 components in the optical domain, electrical domain, binary and memory, which you can use for designing your system, as well as you characterize or view the performance, like represented like what we call them visualizer, which is actually equipment in the field. Now, also we have an OptiSystem example library, which is a huge example library, mainly used for guiding the users how to use the components as well as to build on it for the representation of the system. So what you can do, you can use these systems and plug in your BIC instead of the components used, for example, and do your analysis on it. The other part of OptiSystem software capabilities is the integration between the internal software packages, which is the other 8 software packages from grating, fiber, mode, FDDT, OptiInstrument, which can enable, as Flurin was saying about taking measurements from equipment and then load it into system and do kind of simulation on measured data. Okay, and then the other part of it is external software integration, and that can be done through the MATLAB component, the C++, Python, as well as Scilab. And then the other part of external software we're working with is Lucida, which is actually Lucida, the EPCAS software. So you can design your photonic integrated circuit in their EPCAS software, and then you can do the simulation in their CAFE, get net lists, and then load it into this component, and we can use it for system characterization. In fact, we have 2 videos in our YouTube channel, which you can view on how to use ring resonators as well as cross-connect switches based on designs in EPCAS software. This is now talking about the transmitter structure. So, for example, what is being simulated for representing the receiver side, you have the modulator. So you have the JDS of the modulator, you have the MUX, and they can be represented in the OptiSpace, as you can see here. And also you can have the receiver side where you have the multiple channels coming into the ring resonator, and you can demultiplex them to the desired channels. Now, as I mentioned, you can do the simulation on OptiSpice based on the S parameters you extract from OptiMode or from other third-party software and plug them into the SPICE software. And then you can get the netlist and use them in OptiSystem software. And the presentation, as you can see here, you can have these components from SPICE and then in the netlists, and then eventually you can build. Here we have on-off keying modulation, where you have pulses on and off on the modulator externally, or you can do them through the components. And then you can do the lasers. You can have any type of lasers from DFBs, VCSELs, LEDs, whatever the type of lasers. And then on the detector side, the receiver side, we can have different types of photo detectors, like could be BEN, ABDs, single photon detector, depends on the application you are covering. And then you can do the monitoring using different instrumentation in OptiSystem software. So some of these analysis, like for example, you look at the spectrum analyzer and then start to analyze the system in terms of isolation for the ring resonators, how is the isolation between channels and how is the insertion losses and so on. And also you can look at the eye diagrams and analyze the BR. So more details can be actually seen if you are interested. Basically what we need to kind of message here, hopefully from this presentation, is to kind of get big designers to augment their system characterization to this flow. And then also we are part of our development here at Optiwave. We are adding up into our software BTKs, which coming with actual measured data for the devices and integrate them with the software to allow smoother presentation, like integration between the devices and the system characterization. So if you have any question, please don't hesitate to contact myself or my colleague Scott, as well as you can send the emails to our support for any question. We'll be very happy to demonstrate the software, depends on your application, and show you how to go through the whole process. Thank you very much for listening.
Thank you, Ahmad. Thank you very much for your presentation. Any question for Ahmad? So we have a question from Mike Michelson.
Sure.
Hey.
Yes, from Bright Photonics. Hello.
Thanks for the talk. I was wondering about OptiSpice, do you use the normal Spice netlist format or is it modified?
It's the same netlist format, yes. It's a standard format.
Okay. Yeah, that's it. Thanks.
Thank you, Mike. Any other question? Yes, Sophia, please, from CatFem.
Oh, hello. Yeah, sorry, this might be a stupid question, but with the MATLAB component, does this include Simulink when interfaced with Simulink?
So the concept of the MATLAB component is you can do whatever you need in on math work software, but the important part is the input signal coming, for example, from Optiwave, pass it to MATLAB, so you can do whatever you need to do in MATLAB, and then once you finish that, you pass your output signal to OptiSystem to continue. So in what has been happening inside the MATLAB is, for us, is independent. We don't see it. Is the most important thing is the signal structure between the input ports and output port has to be kind of preserved to be able to continue the simulation beyond the MATLAB component or the Python component.
Okay, understood. Thank you.
You're welcome.
Thank you, Sophia. Ahmad, how well are you connected with the PIX European ecosystem?
We are pushing towards that, and we have lots of communication with fabs and with other EDA companies. We are trying to integrate, and we are trying to make sure that we get like devices which we can use into our software. So we are looking for more of those, but we are slowly going that path.
Okay. So we have a physical event dedicated to PIX, at Epic. I don't know if you already participated to one of them.
I watched them, but we didn't present. But would be nice for us to present there.
So,
would be
yeah. So we'll check, with Ivan. Ivan is in charge of, PIX technologies, so we can check with him.
Sure.
Thank you, Ahmad.
No
Thank you
problem.
very much.
Thanks for listening. Thank you for everyone.
Thank you. So let's welcome our next speaker, Oliver Faehnle, CTO at PanDao. Hello, Oliver. The title of your presentation is the Smart Optics Factory, Bridging Design and Manufacturing, the next level. So please, Oliver.
Okay. Can you see my screen? Yes.
Yeah.
Yes. Thank you very much, Jeremy, for having us here. And we are a small company, but we do some crucial things actually in digital twins. And I would like to talk a little bit, not too long, about digital twins, because the way our PanDao is working is strongly influenced by the analysis what type of digital twin we are handling. So if I move there inside, maybe just one word before, I'm for 30 years in optics fabrication and design at the very interface between Flurin and all the optics fabrication people who have to make that happen. And this trains you very harshly as a human being in thinking in a methodological way, analyzing situations. And that is exactly what you need to do when you handle digital twins. So I will talk about complexity of digital twins. Actually, we had our digital twin is positioned at a certain level of complexity. If it would be a little bit less, it wouldn't work. Nobody would like to have that. If it would be too much, then it's also, again, not working. That's why I asked you, Flurin, about this complexity things. So let me start about the Smart Optics Factory. What is that? That is a factory that runs digital twins at the exact level of complexity they need. And then within a factory, that's much more than just one process. Then you have several digital twins. And if you understand how they differ from each other, then you can tell them how to communicate with each other or how to not communicate with each other. And that generates strength or weakness in digital twins. And PanDao is one of those digital twins. And we run that in 3 different levels. And I will show you. Okay, so basically, digital twin is standing on data. In real life, we have optical designers, optical manufacturing. If this is, no matter if this is EUV or infrared, you have to have at the end of the day a machine that generates the device, that performs in a way the designer wanted it to have. So let's have a look, just a short glimpse. I have only 8 or 9 minutes time to talk. So what I want to transport is the different digital twins and what PanDao is doing and how we are using that. So not to repeat everything, and Flurin beautifully defined that. Basically, a digital twin mirrors the real world. And in order to mirror the real world, you need to translate, like from English to Chinese. You need to translate the real things that are happening into the digital world. And then you have to have access to the real world. And that is a crucial interface. And there you can measure data and use that. You can live stream data and you can train data. And then we have different types of digital twins. And if I do that only in 10 seconds, then I would say, well, they differ in the parameters. Like, what do you want to use this twin for? Light manipulation, the ray tracing, or the diffraction optics effects, if we stick to optical design. And there are many different parameters. And the way, depending on the parameter, you need different approach of your digital twin. They also differ in the application. Is it for optics performance? Is it for manufacturing quality, what we do? Or is it for factory workflow without any physics? Then you have SAP maybe. And so that defines your digital twin. And they differ in the process analysis. Are we really finite element checking material response to something, or computational fluid dynamics? Or are we just generating a data cloud and teaching that through AI? Then the last one, the way we take the data in. Are we training our AI with a data cloud? Do we use rules? Do we use know-how? And do we use even a communication information from a different digital twin who helps me, being a digital twin, to become even a little bit more complex? So these are the different ways, and PanDao is monitoring the manufacturing quality, reading in optical designs of systems, and we are doing that on a quite complex level, the workflow level of fabrication chains. And we had to sharpen this very accurate to be able to generate that and to run that in industry. So inter-digital twins communication is a really hot topic because there is quality maintained or lost. And in theory, it should even level it to a higher level, like a multi-agent system running in several AIs in one thing. So let me focus on optical design and producibility. So if we have an optical product, those beautiful 3 circles you see here, and then we can spread them out. An optical product system has a performance, has a layout, and has to be manufactured. And these are 3 different languages which we speak, like throughput, market price, and so on, and types of optics and types of technologies. And if we have a look, then we all know that there are beautiful digital twins existing, connecting the layout and the performance. The optical design softwares, balancing performance and system layout, whether that is a meta surface or a diffractive or a refractive optical system, they all perform and have to do something like MTF. If we have a look at the last thing, the manufacture, then we see very well dedicated stuff like plasma, fluid jet, ion beam, and whatever. And it's a big mess. There are 360 different technologies, different physical effects, different solutions, different level of TRL level of ripeness, industrial ripeness, and so on. So what can we do with that? And if we went there inside and had a look, and well, nobody needs a single digital twin for one technology. That's nice. If you can model your polishing process for a professor in a university. In industry, we need the whole thing. So we went a level up and managed to model the whole fabrication chain. And well, how does that work? If we are really doing that, and so you can level, as Flurin showed in one of his slides. I will show at the end also a short slide to that. Once you have the layout optimized for performance, that does not mean that it's also optimized for manufacture. And if you have here a digital twin connection, then you can have a whole balancing from performance to manufacture through layout. And that's what people are aiming on when they are using us, the digital twin that reaches from here to there. So basically, like Star Wars, it's everybody wants to have the best design. And for the best design, you need to have a producibility analysis, and then you need to optimum a fabrication chain. So if you manage to have your optical system described in, for example, ISO or MIL, then you feed into a PanDao system, and there are 360 technologies digitalized, and they are digitalized in a way that they can communicate with each other on their level, and they are fighting with each other to be allowed in the best fabrication chain. And the best chain swims out of the swarm of fish and is not getting eaten by this barracuda. And that's what we show at the output of the best fabrication chain. So the digital twin of this PanDao works on 3 different levels. We can do that because we have digitalize those technologies like IBF, diamond turning, precision glass molding, and classical polishing, or iron beam, or so on. And they perform and they communicate on their technology state-of-the-art way. But we can also go closer to an optical workshop and read in the machinery. And then you have the old machine, the new machine, the big and the small one. And they are entities and compete with each other. And this is on the shop floor level. And then suddenly you need many more smaller digital twins, like the one for cleaning, the one for automated interferometric measurements and so on. And so this is a shop floor level digital twin, and that still can communicate, because maybe they have a diamond turning machine, and then they can communicate with out in the market. And then you can benchmark this digital twin with that digital twin and get out information like, we better buy a new machine. Very simple outcome, but financially and risk analysis quite important. So with this, you can, of course, compare different optical designs in terms of producibility and cost. And you can read in optical elements, and then you see a technology chain. We modeled chains, and then this is, for example, the 5th lambda A-sphere. And if you then go to 10th lambda or whatever, you can change everything with one click. Then the technology chain answer is different from MRF to IBF and some different costs. So with this, you can do a life cycle analysis, like you want to know during the prototyping what's the best chain and cost and risk, and for the serial fabrication, and where is the technology switch happening. If you know that, you can plan, and you can, for example, as optic designer, Flurin, you can compare then a glass system with a Xeonex plastic optics system. And then you see there are areas, this is a logarithmic the cost, logarithmic the numbers, and then you see where they are quite close to each other, and you might want to jump for better quality and pay for that a little bit more. Okay, so digital twins communicating not only between those technologies on a manufacturing level, but of course also with the digital twins from the optical design. And Flurin had this beautiful slide in the beginning, and I want to grab there, because you simulate and you digitalize the performance and the layout of your microscope objectives, and then you end up with 2 different qualities, and they impact with.
Sorry, Oliver, the sound is not. No, the sound is not very good. That's why I'm stopping.
Oh,
yeah.
Okay, I don't know. Can you hear me?
Yeah, now it's better.
Okay, maybe my finger was sliding a little bit. Okay, so you have 2 solutions which you consider, and they differ in performance, but they also differ in risk in manufacture. So you can give these 2 variations to PanDao, for example, and then analyze it, and then feed that back, communicate that back. And this both sides information can be used in the future for an even higher level optic design, where you have 5 versions during your Monte Carlo simulation, possible, and then you weigh them with the manufacturing risk for the same performance, for example, and you go in one direction further that is optimized for the performance needed optically and the manufacturing risk we are prepared to take. So with this, you can then, for example, say here, this version will cost you X more, and you need a technology your supplier has not in-house and things like that. We are located in Switzerland, in St. Gallen, and our company name is PanDao. And if you're interested, we can show you some of your optics, what we can do with that. We do digital twins of optical workshops of companies, and then you have with one click your whole optical workshop performance and get the best fabrication chain through your machinery and can benchmark that with what's available out in the market. These are some customers who are using us. So thank you very much for listening. And that's what I wanted to tell you about digital twins.
Thank you, Oliver. Thank you very much for your presentation. Any question for Oliver? Oliver, can you elaborate a bit more about the accuracy of the comparison of your 360, techniques of manufacturing, and especially when you integrate an innovative solution in terms of how is it accurate?
My answer is twofold. From the technology point of view, we have to have data cloud quality. That means the performance of those single fishes, those technologies, they need to be able, in order to be able to communicate, they have to fulfill a quality level. So we assess new technologies when they happen or when they get updated on machines in a way that we observe them. And that's one thing. The second thing is the absolute cost. That's a problem because we don't know the cost structure of a company. So the digital twin that runs the optical shop, that is better than 10%, 8% accurate. If you go for the general out in the market, then we calculate actively the cost, and we take into account the salary of an engineer or a technician, we assume how many uptime your machines have, and for what was the investment bank deal, like interest and payback time over years for when you bought a certain machine. This differs. A big company and a startup has different bank deals, right? So we can adjust that, and for the general with a certain accuracy, but for workshops, we are about 10% accurate.
Thank you. Oliver, can you share again your slide with the list of clients that you have? And then Ahmad, you have a question, so please.
Yes, thanks, Jimmy. Yeah, nice presentation, Oliver. I have a question about the training process and the machine learning or something. Like the data which you use, is it used for prediction? Like, for example, when you get data for these lenses or objective lenses, do you use them for prediction? Like if you have certain condition, this is your performance, or for other purposes, the training?
I don't understand really your question. You have to have defined your optical system on a level like technical drawings, optical design. You
Right.
need to have, yeah, and then?
Right. And then you get the data, measured data or something, right? And then you do training, or the training is for something else, not on the data which you have.
We train and generate the manufacturing technologies, and they don't know about the lens, so to say. The lens is the boundary condition. The lens is our MTF performance, and the grinding, the polishing, or the precision glass molding. This is our for the optical designer, the lenses. So this is the ray tracing. We ray trace through a sequential series of fabrication technologies. So we must ensure that the fabrication technologies can communicate with each other. But it's prediction from the lens. The lens gives us defines material, tolerancing, geometry, and dimension. And within this, certain technologies are able to do something, and then they fight to be in the fabrication chain.
Okay, now I understand. Okay, because I'm just comparing it to kind of our software, because our software, when you do system characterization, you can get lots of analysis of your parameter changes, and then you can train the system, and then eventually provide you with a prediction that if you have these conditions, this is your performance, basically. So it's kind of different. Okay.
I see. Now we have a kind of floating system. They try to be there.
Okay.
That's
perfect. Thanks, Oliver.
Thank you, Ahmad. Yes, Tolga Tikin from IZM.
Hey, can you hear me?
Yeah.
Oliver, I'm wondering how you deal with the IP. So can you elaborate somehow, coming from the technology, what is the interface and to the customers and back to the foundries, how you deal with that?
So with IP, you mean the IP of the optics you want to check with PanDao, right?
I mean, actually, the companies have the technology, right? So that means all those processes and so on, even though it's somehow reflected in the digital twin, the material data, the process data, and so on, that belongs to the company somehow, to my understanding.
No. We are not a Wikipedia. We have no suppliers registered with PanDao and show their performance. We physics simulate what diamond turning can do on an ultra precision machine. We do the same for plasma polishing, and then we describe and learn and know those technologies, and then they want to be applied to generate this aspherical lens from germanium, and then the diamond turning is doing a better job than an MRF in this case, maybe, and then that's the solution. So it's not a lookup cloud from 200 Wikipedia. I would be much more rich if I would have done it like that. We didn't. The IP from the optics is completely safe. As you see, we have also some defense and automotive companies who are running us.
Thank you.
Thank you, Tolga. And thank you again, Oliver, for your participation. Thank you.
Thank you.
So let's welcome our next speaker, Nikola Nedovic from NVIDIA, Senior Research Scientist, and he will talk about modeling and optimization of dense wavelength division multiplexing links. So Nikola, are you here? And if yes,
yes. Just 1 second.
Yeah.
Okay, let me turn on sharing.
Oh, by the way, we had a question from Mike for you, Oliver, I guess. Mike, if you want to ask your question directly, you can send a message to Oliver in the chat. I didn't see it, sorry. So please, yes, Nikola, you can start.
So let me know, can you see me, hear me? Is everything okay?
Yes, all good.
Okay. So my name is Nikola Nedovic. I'm from NVIDIA Research, and I'm going to talk about sort of a supply side of things here. So use of photonics and simulation and system level or link level simulation of photonics used to build data center, or that can be used to build a data center and design systems. And I want to say that this is research output and research work, and is not really. I'm not going to talk about any products or any plans for products. So just keep that in mind. As an introduction, I want to show some computing trends that everybody is aware these days. So machine learning and AI in general, drivers, well recognized drivers of computing systems today. And you can see that as AI took off about whatever that is, 14, 15 years ago, demand rapidly accelerated, which is shown by this orange and red lines. So we see the CPU performance scaling that doesn't really track that very much. And in contrast, you can see that accelerated computing, GPUs, XPUs, and so on, has been going on, and it's actually quite impressive. But even so, it does not track the scaling of the computing, and as a result of that, you see a growing and growing gap, which is really the reason why we're building larger and larger computing systems today. So we have to come up with this gap, with this difference in more and more computing unit systems, servers, racks, and so on, and we have to connect them. And to solve that problem, we can turn to photonics, as we all know. And here in particular, I want to talk about dense wavelength division multiplexing as I think ideal choice for this AI or more, basically modern AI systems. So the reason is that if we have the lasers available, this is a big if, and people are working on that, but we're going to leave that aside for now. If the appropriate or adequate lasers is available, one key benefit of these systems is that we can export all these high-speed portion of the link. So we're talking about some hundreds of gigabits per second, terabits per second, or so on per link. We can export all that in optical domain, and electronics never sees it. So anybody who tried to design electrical link running at 100 gigabit per second or higher knows how huge a benefit that is. And as a result, we can get many benefits in terms of throughput, energy, area, latency, and we can pack these macros in a very small footprint, allowing us even to go to co-package optics and optics interposer in the future, and that even further gives us even further benefits. But the downside of the whole setup is that it's a very complex system that I'm going to talk about in next slides, and it really requires detailed and accurate link modeling. So in particular, crosstalk is a first-order phenomenon in these systems. And by crosstalk, I mean optical crosstalk between adjacent or maybe not so adjacent channels. And in this slide, I intentionally try to make or try to show it's look busy and maybe confusing, but this is really, as I said, intentional, just to show how many different components, design considerations, metrics, and so on are in the play, and each affects each other, and each affects the metrics that I show here in the center, and there could be some other metrics as well. So, and the main point really is that design space is vast, and that we have to have a tool to make these trade-offs and make these choices. And this is a high-level picture of how our internal statistical link tool works. By no means is the only way to do it, but this is how we handle it. So we first capture the behavior of individual components, and I'm going to talk a little bit more about rings later. But in general, we capture those components' behavior in time domain, whether it be optical components, electrical components, whether it be measured, simulated, high level, low level, it doesn't matter. Just as long as we have a description of its behavior in time domain, we can then proceed to building a link level step response matrix, what we call step response matrix. Basically, this will give us a response to any output of the system, to any input of the system. It's a big kind of MIMO system that captures all intended behavior, all intended input to output transfer functions, as well as all the possible crosstalks and all the possible side channels interactions in the system. So when we have that, we combine it with the data pattern probability and the noise to create statistical eye diagrams. And from these statistical eye diagrams, we can get things like eye openings, and in combination with the power model, energy efficiency, and any sensitivities of these metrics to any of the input parameters that we can wiggle, we can optimize. Here I show some details on how we deal or how we estimate the device level models, and I show this for example of micro rings, and essentially what we do is we do our own sort of encapsulated inline simulation of the ring. So basically what SPICE would do, kind of, but just stripped of anything that is unessential, to minimize the computation time and allow a quick but accurate description of the behavior on a time domain level. So we do the computation in a complex domain to keep track of the light phase information, which is really peculiarity of the light here, or actually anything oscillating basically. We specifically separate low to high and high to low responses to capture nonlinearity, because these devices are known to be nonlinear at this level. And I want to point out that really anything complex, things like power buildup, overshoots, optical bandwidth, and so on, is an emergent behavior. So we don't really specifically model any of that. We just say every component in this device behaves so and so, calculate what the output is as a function of input, and put them together. And as a result, we get these overshoots and bandwidths and so on. So next, we use these responses to build a statistical eye diagram. And we do this by convolving impulse responses of all these components that we calculated from every input to every output. And we do that simply by having some way of representing how our system looks like. So what comes first, what comes second, because this is sort of one-dimensional system, and we use that use that fact. So we have some sort of computation in non-intensive way of building this step responses. So, for example, from the second input to the third output, we we traverse basically this one-dimensional graph, and we do the convolution of all these components, including electrical device first, and then optical device, a ring in this case, going from electrical input to optical output, and then hop one by one, accounting for all the non-idealities and losses, again, from optical input to optical output and so on, until we get to the output of the system that we're interested in. And we add the effect of the random noise by convolving the noiseless histogram, which we build by doing this, with the noise PDF with the appropriate transfer function, which is also what we calculate on a side. And this depends on the point of the noise occurrence. And at the end, we just, depending on this time offset that we calculate this for every time offset in the eye, in the unit interval, and we simply just pack them together, pack these histograms together to get statistical eye diagram. And with the help of, as I said, power model, we can get pretty much everything that we're interested in about this size. So we can get noise effect, we can get eye opening, horizontal and vertical domain. We can get energy efficiency, and we can get the sensitivity, as I said, of all these metrics to all our inputs. So next few slides show some examples of what we can get with this tool. I'm not going to spend too much time, but this is just an illustration. So, for example, if we have a link that is already architected, meaning we know how many input channel, or how many channels we have, what is the data rate, and so on. We can use this tool to get the, for example, quality factor of different of the transmitter and receiver side. We can do this by some sort of complex optimization, or here I just show some really brute force 2D sweep, and we simply pick the best one of the metrics that we're interested in. Another example is some link simulation for some, in this case, 800 gigabit per second fiber with some, there's many assumptions here on what kind of devices we have, what kind of electrical circuitry we have, what bandwidth, and so on. But you can see that you can get a very simple, very quickly and very simply estimation of the best, let's say in this case, energy efficiency as a function of data rate, as a function of what kind of, do you use an equalization, do you use some advanced device ring modulators, some kind of complex filter, optical filter, the receiver, and so on. And a third example I want to highlight is the comparison of what actually everybody does, is comparison of non-return to zero, so just one symbol per one bit per symbol versus 2 bit per symbol PAM4, which is encoded in intensity. And we show that in this particular system, PAM4 is not really the best option unless, and the reason really is that these links are what I call amplitude starved, and you really want to do whatever you can to optimize or to increase the amplitude of the receiver, which is then what the noise acts on. And the PAM4 simply kills that metrics by a lot, by 9 dB or actually more in practice. And really, the only reason that you want to use PAM4 is that for some other reason you're forced to work at really high data rates where other things like electrical circuits blow up, and you have a very difficult time, and you have to spend a lot of resources, energy, area, and so on that. This is where PAM4 actually can buy you something. But if you have a freedom to choose, use the WDL system and choose whatever data rates and number of channels, this is, according to this study, it's not competitive compared to the NRZ. And as a conclusion, I'm not sure how I'm doing with time, but as a conclusion, I show you a tool for design optimization of DWDM links that you can use to optimize architecture, choose device parameters, low-level device parameters, and their effect on the whole link. And also very important, I didn't talk about that much, but you can gain insight on the design and identify most useful directions. So is it better to invest in a better electronic or EIC faster process, or is it better to work on multi-wavelength lasers, or whatever is gives you the best or the highest sensitivity to your link performance. So I also show you some examples of how the tool can be used and what are some of its outputs, and some just to illustrate the utility of the tool. And this concludes my talk. I hope I didn't go over time. I didn't really track. I'm sorry.
No, all good, Nikola. Thank you very much. So a question for Nikola. Yes, Ahmad, please.
Yes. Hi, Nikola. Thanks for the presentation. I'm just interested because the work you did is very close to what we do at Optiwave, and just wanted to ask, I mean, your simulation, is it an in-house development or a third-party software?
No, this is all our development from the scratch.
Okay. And like, I mean, because this is something which is part of maybe these kind of meetings, you'd like to kind of establish collaboration and discussions. I'm not sure if you are open for doing that. And we can do, for example, demonstrations, show you the capabilities of our software, like mainly OptiSystem and OptiSpice, which fits very well with what you're doing.
Yeah, it's always interesting to see that, and just at least to compare the notes. But it would be nice to talk to you about that.
Sure. I'll send you a message on then to exchange emails, and then hopefully
Sure.
we can. Thank you very much. Okay.
Perfect. Thank you, Ahmad. Any other question, comment? And if not, let's thanks Nikola again. Thank you, Nikola, for your participation and for waking up so early. So thanks
That's
a lot.
okay.
So now let's welcome Lieven Penninck, CEO at PlanOpSim. Lieven, you will talk about unlocking the potential of meta-optics system by multi-scale modeling.
Yes, thank you, Jeremy, and thanks for this introduction. So indeed, I'm Lieven Penninck. I'm the founder and CEO at PlanOpSim. At PlanOpSim, we focus on one specific type of optic, namely meta lenses and meta surfaces. So from your different educations, I'm sure you've all been introduced to traditional optical systems that consist of many lenses which have been optimized to work together to deliver you a certain MTF or a beam shaping performance. All of this is very big and bulky and not really very well suited, for instance, for miniaturization and integration on a very large scale. And to improve on that, a new technology was put forward called meta lenses and meta surfaces. These use nanostructures to locally manipulate the light and shape it in any way that we want. What that allows is that we can then finally create components that are very difficult to create with conventional optics, making the optics smaller, arrayed in large areas, for instance, making miniaturized or simplified applications. And all of this is manufactured and compatible with the technologies that we all know from this semiconductor industry, namely etching and lithography. Everything is in dielectric or materials. There's no organics, or they don't have to be any organics involved. And this might sound a bit futuristic, and I have to say it was futuristic 10 years ago. Nowadays, these components are found in some high-volume consumer electronic products, for instance, as you see in this teardown that was done by Yole Development. The meta surface there is used to replace several conventional optics to make a complicated functionality in a single piece. Now, what is PlanOpSim? PlanOpSim's role in all of this is to take the optical designer's role, which usually was based on geometrical optics, and bring them into this new world of wave-based and meta-surface optics. For that, we provide simulation and design tools to model the whole workflow from start to finish. So going from the nanoscale, where we optimize these structures, to organizing them in components, to then integrating these components into systems. And the workflow looks a little bit like this, and I'll maybe talk a little bit about really why we need a multi-scale model to design such meta-optics-based systems. So the nanostructures, they are tiny, smaller than a wavelength, so we need to model Maxwell's equations in full in order to accurately model them. Now, any one of you, and we've seen introductions of FDTD, for instance, here earlier, knows that these simulations take a lot of time. They are not feasible to do for the millions of structures that you have within a meta lens. So for that, we go to a next scale of simulation where we have a phenomenological model based on a database or based on a pre-trained or maybe even analytically derived function of what our meta atoms are capable of, sometimes also in concert. And then we bring them to a component level on which there are millions to billions of these structures, and we calculate using wave optics what is their performance. That's still just a single component. If we want to think about systems, we have to couple that all the way back into the system, which is really that large that in a lot of cases it can even be communication between satellites. It's that large that really only ray tracing will work. And our PlanOpSim software platform allows this end-to-end simulation of meta surfaces from the nanostructure scale to the large scale. It is completely automated and can be addressed via an API, so it's very easy to integrate, for instance, with other running or updatable systems that were introduced also by the previous speakers. And you can step in and out of this workflow at any point. So if you have some proprietary algorithm that you would like to use instead, that's no problem. You just plug in your custom method, step out of the workflow, do what you need to do and step back in. And like this, we can very easily integrate a detailed optical multi-scale model also with all kinds of other optical engineering. Diving a little bit into the different models that we use and why we use them. On the nanostructure scale, we use rigorous coupled wave analysis to solve Maxwell's equations. There are many other ways to solve Maxwell equations. For this particular type of structure, we found that RCWA outperforms most other methods in terms of speed, but it is giving the same results because they are solving the same physical equations. Of course, this is not a general property. It just happens to be the case for this type of pillar and other small nanostructure types of calculations. It might be entirely different for a PIC, for instance. And when we have these libraries of structures, we can then start integrating them into components and make, for instance, a lens. Here I recreated a simple, famous design example from the Capasso group, for instance, where we use these rotating pillars to control the phase and create a polarization conversion and organize them then into a concentric phase front generating a lens. So we can easily create this and in short time using our cloud multi-scale platform. So this is all nice. We can simulate some things and it looks good. We have colorful pictures, but how does it look when we start actually making these? And we have made some of these components together with our partners. So this is a demonstrator that we made together with Moxtec. So we did the design using PlanOpSim software. Moxtec manufactured the pieces. And what you see here is a polarization multiplexed hologram projection. So we have a single meta surface here marked as MOE. If we shine on that with a laser, it projects one image. If we rotate the polarization by rotating the laser or by changing a half-wave plate, for instance, we are projecting a different image in a very compact way. So really I cannot use the word system because there's really only one surface doing all the work. If you had to do this in a traditional way, you would have to do this with multiple components. So this is much more compact. The picture on the left doesn't do it justice. You can get it about as small as your finger if you use some 3D printed holders together with a VXL and the component. We can take this further as well and use more complex manufacturing within the tool, interacting between new capabilities that manufacturers are making. For instance, the ability to have both in-plane control of the shape and height control. So we can combine the design approaches of a conventional diffractive with a meta surface. PlanOpSim used then our software to design it. Skill has developed the process, and here are the results of that. So we can directly imprint these structures on large areas. You see the one here, that's around the 12 millimeter size, which corresponds to over 1 billion pillars in that design. So this is really an enormous scale that you would not be able to feasibly manufacture with all the calculate with all the compute in the world using any FDTD platform. If you're this world of nanostructures is very new for a lot of optical designers. So we borrowed the concept from the electronics world and the PIC world, known as PDKs. So designers can now in software select PDKs which have been pre-optimized by manufacturers so that they can directly use these designs, these pillars in their designs without having to worry about the manufacturability, because this has already been optimized by the manufacturer and is guaranteed by them that they can make these structures into their systems. I will skip over this slide in view of time. So far, I've only talked about components. Meta surfaces are just an optical component. We always need to integrate with sources or with detectors or with other meta surfaces or classical refractive lenses. For instance, if we're trying to couple into a waveguide, or if we are trying to make color filters here, like in this example, for an imaging system. So we use a standard ray tracer to design an imaging system, in this case here a simple telecentric lens, and then we use the unique capabilities of the meta surface to split the color in a multiplex design, sending red light up, for instance, here to this subpixel and blue light down to the other subpixel. This is a behavior that is unique to meta surface, so it's not possible to directly ray trace this. For this, we have phenomenological models that come directly out of our ray tracing link, which you can then plug into different ray tracers like TracePro. And I'm excited to say that very soon there will be other ray tracers as well that we will announce. We also have a direct SDK so that you can connect this to your own programs if you have some in-house ray tracers or other models, finally allowing you to use the meta surface then in a system. If we then go one step further and think about design for manufacturing, then we know that as we manufacture millions of these pieces, for sure they are not all the same. We will have typical manufacturing effects like sidewall angle, shapes deforming, local proximity corrections that need to be done in order to control the shape. What is often nebulous is what is the effect of that on the optical system performance. By connecting the whole chain from the pillar shape to the meta surface and the optical system design, plugging in those exact changes, we can model what is the effect on the optical performance. So not just on some abstract phase function, but actually on the performance of the system. So for instance, in this case, this is a light collection optic where we want to maximize the blue part, the collection efficiency, and reduce the orange part, the parasitic or the stray light that's hitting our detector. And when we look here and we simulate that, we see that some manufacturing changes, they all reduce the performance, but some changes are worse than others. For instance, decreasing the pillar size leads to a stronger increase in the stray light than increasing it. So this gives you crucial information in the manufacturing that probably you want to err on the side of caution, a little bit too large, so that when your natural deviations occur, you have a better overall yield of your system, because you are trying to align hundreds or maybe more of these little of these lenses, for instance, in some quantum computing applications that's very much needed. And all of this is really made possible by the fact that our software is completely on the cloud, can be integrated and stepped in and out of at any moment. And I'm really excited to find more applications of this and collaborate with you on that. And with that, I'd like to wrap it up and restate our mission. PlanOpSim wants to be the tool for meta optics development, and we're very excited to talk to you and work with you on all kinds of applications where you want to use meta surfaces. Thank you very much.
Thank you, Lieven. Now time for question. Any question? Lieven, you cover, the visible and near infrared wavelengths. Are there any plan to go into more sphere wavelengths ranges?
Oh, we cover much more. So, for instance, this application was in fact a long wave infrared design.
Okay.
So, from a principle standpoint and a design standpoint, there is no restriction on the wavelength. Of course, if you go, for instance, into the EUV, you will need some way of making structures that are sub-wavelength relative to EUV.
Ahmad.
Okay, thanks, Oliver, for this good presentation. Question is about adaptive optics for free space optic wavefront distortion. Did you do any work on it using your software for designing these things?
We have not really specifically worked with this, but I think there is a lot of potential for this type of component, because where a meta surface excels is in making complex wavefront corrections that would be difficult to make with traditional manufacturing methods. So if you could, basically for the meta surface design point of view, if you can tell me which wavefront you need, it can be manufactured, it can be created, and the crazier the shape, the better in a way.
Okay. That's good. Okay. Well, I'll contact you with that for sure. Because we have lots of application for free space optics. Yeah. Thank you.
Thank you, Ahmad. And we have a question from SPIO Systems from Andreas Holm. Andreas, do you want to ask your question by yourself? Okay, I will ask.
Can you hear me?
Yes. All good.
Sorry. Just a quick question. I was curious about how you can model like imperfections in the manufacturing in the PlanOpSim software. Like, for example, like rounding of corners of nanopillars and stuff. Can you model how that impacts system performance?
Yes, we can do that, and we have done that in several applications. I can send you some details of that. So in the case here, for instance, it was differences in the diameter of the pillar. But essentially what you need is a model for each deformation and what its effect is on the optical response locally in your metasurface. Then you have millions of these pillars, so you start locally replacing them, and you see then what's the effect on your wavefront, and ultimately cascading that forward into your system performance. But you need these multiple scales of simulation to be fast enough so that you can run through these different cases. So if you do a Monte Carlo, for instance, you end up with 100,000s of different lenses that you are simulating. So if you try to brute force your way through that, it won't work.
Thank you so much.
Thank you, Andreas, and thank you again, Lieven, for your nice presentation. Thank you. So now we welcome our last speaker of the day, Dominique Bonnisseau, Business Development and Product Management at MIMOPT. And the title of your presentation, Dominique, is Shaping the Future of Optical Communication Systems. So please, Dominique, you can start. So we can't hear you, so maybe you are muted.
Sorry, do you see my screen?
Yes, we can see your screen and hear you well.
Okay.
Okay, we can't see your screen anymore. Okay.
Okay. So why it doesn't work? Okay. So thank you for giving me the opportunity to present the new and amazing optical communication system software for fiber and free space we will see later. So the MIMOPT company was created in 2021 in Paris. And the team is made up of experts in the field of optical communications, of course, and photonic network technology. More than that, optical architects, digital communication, and optical transmission focus on digital processing and high optimization. So the CEO of the company is associate professor at the Telecom Paris Engineering School. This company developed at the beginning some simulation for several customers, very specific simulation, and they discover over the year that they can make a complete simulator and digital twin. So the first on the top left is an automated solution, because traditional modeling are slow and delaying critical network decisions. So it's automated simulations accelerating predictive analysis. So it's very important to understand that we will expect performance depending on the condition. It's very critical for free space communication, ground to ground, ground to satellite, and satellite to satellite. So it's very, very important in that case. The second point is we mitigate the risk and the uncertainty in the network upgrade. So changing existing networks or developing a new one is very risky and very expensive when we implement the modifications on the new systems. So we can make the digital twin in advance and then see how we can implement it. And of course, our customers are saving a lot of money and time to implement those kind of networks. And of course, we ensure the interoperability, which is now critical. So we can use every systems from vendors, emitter, receiver, transceiver, or whatever, to simulate all the network and the performance. At the end, we offer AI solution. For the moment, is focused on the customer challenges. So each time we have issues, we offer a solution on this. It's not a general one. It's very focused on specific problems. So our customers are, of course, telecom operator. We are working with Orange, the famous French company. Of course, we are working with equipment vendors because they can make and integrate in, I would say, a typical or in, typical network. They can insert their own product and see how it works with other vendors. And they can find sometimes some advantage, or they can find some change for the future R&D development. We are working with energy provider. They have a lot of fiber network systems, academic institution to work on advanced systems and network architectures, transport company, for which the networks is really, the transmission networks is really critical and strategic, semiconductor and PICs, and defense and government. We are working with some defense organizations to see how we can provide and maintain the networks in the right performance. So I will not describe this picture, don't worry about that, it's the last presentation, but we can simulate all of those networks and parts of networks. So you can see free space, satellite, ground, fiber, networks, or whatever you want to make for your systems. So we have two use cases. The first is a network that you can see on the top right of the slide, and using MIMOPT, multi-vendor digital twins provide solutions and simulation to have the right level of quality of transmission. So we can increase the prediction accuracy by 93% and the design margin reductions by 3 dB. It means for sometimes and for some network owners to avoid any huge investment or to limit investments, keeping in the same level the network's performance. And we can validate the right light path validation by 33%. It's a question of time. So faster, more accurate, and less expensive investments. The second one is just free space optical communication between two systems. We have the results and the measurements results, and we made some simulation, and we find equivalent results. It means that the owner of this communication link can anticipate, depending on the weather condition and the load of the network. It was very short, so we offer optical network digital twins, and we are looking for challenging projects, optical fiber and free space optical communication. Thank you for your attention. At the last, you have the communication and the email you have. So if you have questions, it was short because it is the last one.
Thank you, Dominique. Thank you, Dominique, for presenting this interesting technology and company. Any question for Dominique? Yes, Flurin.
Yeah, hi Dominique. Thanks very much for the nice, very interesting presentation. My question was on the optical communication, especially the free space one. You mentioned that you can model fog, rain, and other types of turbulences. Are you simulating the whole distance, and how are you including turbulencing? Are you including an average or taking into account real data from weather forecasts or something like that?
We are using the data available to our customers. So we are using data measured by the weather system. They measure the wind speed, the visibility, the many things, turbulences. So there are some providers on that. and we are using those data. And sometimes, if we do not have those data, we are using standardized data. And in that case, we are looking for measurement data in similar situation. But we are taking into account on all weather conditions.
Very interesting. Thank you.
Very interesting. Thank you, Flurin. Do you know, Dominique, do you know the company Reniwatt? They are making this kind of analysis of the atmospheric condition. They develop a specific system, and they work a lot with companies which are doing optical communication for Earth to space application.
I don't know this company. I know another one named Miratlas, but I don't know this company. So
Reniwatt. Okay,
connection.
Dominique, I switch off your mic because you have an echo. Okay. And do we have any other question for Dominique? And if not, thank you again, Dominique, for your presentation.
You're welcome.
Thank you. And yeah, so this is the end of the meeting. We hope that you enjoy the presentation and the topic that we covered today. If you need to be introduced to one of the participants of today's event, one of the speakers, just let us know. You can send us an email and we'll be very pleased to introduce you to the person. So thank you again. You had also a poll to give us your feedback. And yeah, we stay in touch for another epic meeting. Thank you.
Bye-bye.
Bye-bye. Thank you.
Right.
Thank you.